In previous lectures, we classified states. Now we will extend this classification to Markov chains. First, in a Markov chain, a state J is said to be accessible from a state I, and we denote this as from I we can go to J, if the probability of ever returning to J, or ever going to J, having started in I, is positive. Meaning there is a non-zero probability of getting from I to J. So in other words, Pij of M is non-zero for some M. Okay. Now states I and J communicate, denoted as I and J both go to each other, if I is accessible from J and J is accessible from I. Okay, so a consequence of this definition is if I and J communicate, then A, I and J have the same period. B, if I is transient, then J is also transient, and vice versa. I is transient if and only if J is transient. And finally, I is null recurrent if and only if J is null recurrent. How can we prove this? The proof is going to use the Chapman-Kolmogorov equations, which is a consequence of the definition of Markov chains. If I and J communicate, then there exists some M and N that are greater than 0 or equal to 0, such that we can take the product of Pij of M and Pji of N, and this product will be equal to some non-zero value alpha, because there's a positive probability of going from I to J for some number of steps M, and for there exists an N number of steps N such that I can get from J to I with non-zero probability. So I can always construct this product, which is going to be a number alpha that is greater than 0. So by the Chapman-Kolmogorov equations, Pii, the probability of going from I to I, in M plus R plus N steps is greater than or equal to Pij of M, Pjj of R, Pji of N. Meaning, going from I to I in M plus R plus N steps can be broken down into various ways. There are various ways of going from I to I in M plus R plus N steps. In one of these ways consists of going from I to J in M steps, then going from J to J in R steps, J back to J in R steps, and then going from J to I in N steps for some choice of M and R and N. Okay, since this event is included in that event, this probability is an upper bound on this product. But we can call this product alpha times pjj of r, where we defined alpha above. Okay, and this is true for any choice of, there's a choice of alpha for any choice of r. Okay, so consequence of this is summation over r pjj of r is convergent if and only if pii summed over I is convergent. Okay, because this, since this is greater or equal to this, this is convergent. Oh no, this is convergent if and only if this is convergent. This means by BC lemma 1, remember, J is transient if and only if I is transient. So that's proof of this part. I will leave the proof of this as exercise to you. And similarly, I will ask you to think about the proof of part C. Now, as a consequence of these observations, essentially, these observations say that in a Markov chain, states are of the same type. Okay? So, now, in order to say that, first we need to define a class of states. Okay? Now, I will define a set C of states is closed if basically all the transitions out of each state in this set is to one of the states in the set. In other words, if Pij is 0 for all I in C, J not in C. So basically, when I leave a state in this set, I go to another state in the set. So it is closed. Now, it is a set C is irreducible if I and J communicate for all I and J in the set of states C. Okay, so a set of states in a Markov chain is said to be an irreducible class if all the states in the set communicate. Very simple example. Think of 1, 2, 3, 4 states. These are self transitions. From 3 you can go to 4. From 4 you can go back to 3. From 2 you can go to 3. From 3 you can go to 1. From 2 you can go to 1. And from 1 you can go back to 1. Okay, in this case, do 1 and 2 communicate? No, because there's a way to go from 2 to 1 and never come back. So in this case, 1 by itself forms a recurrent class. If a recurrent class has only one state, we call this recurrent class an absorbing state. Remember the walking off the cliff example in several lectures ago, where the position numbered 1 was an absorbing state. Now, 2, 3, and 4 all communicate, but they are all transient in this case, because once we get to 2, there's a probability that we'll get to 1, and once we get to 1, we will not return to these states. Okay, now we call an irreducible class aperiodic if all the states in the irreducible class have this property. Let me give you another example. Building on this example, again, we have states 2, 3, and 4 as before, but this time I'm going to add a state 0 such that 0 and 1 communicate, and they form a recurrent class. Okay. Now, this is a recurrent class of 2 states. They are both recurrent. Okay. Now, 2, 3, and 4 do not really form a class because they are all transient. In a recurrent class, all states are either positive recurrent or they're all null recurrent at the same time, and they all have to have the same period. So we will now use these properties to start understanding convergence properties of Markov processes.